Hi, my name is Benjamin Capps, and I'll be doing a presentation on computer-generated Mega Man levels. In order to understand computer-generated levels, we first need to understand content generation. Procedural content generation, or PCG, is a way to create video game content, like levels, worlds, etc., using an algorithm. Doing this not only saves money and time that the developers do not have to spend on making each level or world, but it also creates replayability for the consumer. The most common example of PCG being used commercially is Minecraft, where the algorithm generates a seemingly infinite world for players to explore based on a seed. Procedural content generation via machine learning, however, is still experimental. Companies have not yet adopted this way of content generation, largely because it's still being researched. PCGML is data-driven and learns from the data that it's fed. This is where the Generative Adversarial Network, or GAN, comes in. GANs are capable of generating new video game levels by learning the structure of original levels. Essentially, GANs are trained on human-designed level data, which allows them to create endless levels based on the original game, which increases the replayability and eliminates the need for a human designer to create whole new levels. There are two key components to training a GAN. First, there's a generator, the GAN, which is responsible for generating an image based on a randomized latent vector. Next, there's a discriminator, which is trained to recognize whether a given image is real or fake. This summer, we explored PCGML using the original Mega Man levels as data. The video game level corpus contains data representing a variety of early video games using symbols. As you can see here, the pound sign represents a solid block tile, the dashed line represents an air block, the bar represents a ladder tile, and so on and so forth. In order to properly train the GAN, the data needs to be in a numeric format, which explains the conversion to numbers here. On a single training cycle, you show the discriminator some real level segment and tell it to adjust its weights given that that segment is real. Then, it generates some random level segment with the generator and adjusts both the discriminator and the generator given that that level segment is fake. This process repeats until the discriminator can no longer tell whether an image is real or fake, and its decision is no better than a guess. Although random inputs will produce convincing fakes, it takes a bit of work to find non-random inputs that have desirable properties. Then, we use a simulated evolution process to help find the best GAN inputs for creating the kinds of levels that we want. In this case, we want long, beatable levels. This is a visual representation of how we obtain the data from the original VGLC levels. Basically, the black box represents the current segment that's been saved and converted into numbers. Our algorithm then determines which directions are legal to traverse and which are not. In this example, directions left and down simply have no data and can therefore not be used in training. The direction up contains null space, which is effectively useless data that would not only hinder our training process, but also give us poor results. Direction right, however, is traversable and contains useful data. The screen moves one character to the right and saves the data within that box, then repeats the process until the entire level has been traversed. We realized that since all the data was used to train the GAN, we had a variety of struggles. Mainly, the level segments were placed without regard to the direction it's going. For example, the singular GAN might generate a corner segment like this one with a wall here or a ceiling here that would prevent the agent from crossing over to it and traversing the entire level. To help mitigate this, we separated the training data into parts. We trained a separate GAN for every type of level segment. Each GAN was assigned training data based on one of the following segments: horizontal, up, down, and four corners, being lower left, lower right, and upper left, which is not displayed, training a total of 7 GANs. The reason we did this was to avoid bothersome GAN generation and allow for streamlined placement of level segments that the agent can traverse through. After the level was generated, we used a search algorithm called A* to navigate the level and assign it a score based on how far the agent progressed before either being stopped or beating the level. We then used objective evolution to maximize the length of the path the agent took in order to beat the level, thus creating longer and harder to beat levels. Here, the red X's represent the solution path. The longer the path, the harder it is to beat, whereas the white X's represent the searchable area not included in the solution path, so where Mega Man could theoretically traverse to. On this graph, the y-axis measures the solution path length of the best level in the evolved population, whereas the x-axis represents the generation. Each entry is an average across 30 different runs of evolution, which is why there are confidence intervals. The intervals are narrow because of how consistent the performance of each method is. This orange line represents the 7 GAN method data, and this blue line represents the 1 GAN. For each generation, the average 7 GAN value is statistically significantly higher than the corresponding 1 GAN value, meaning that it discovers longer levels quicker and levels are at a higher measure of performance. Thus, we have concluded that the use of multiple GANs is effective when working with training data that contains a variety of different qualities. Thank you.